Hi, this video I'm making for my students who are using Swink et al. 5th edition. This is from chapter 3, managing processes and capacity. So let's do a few problems. All right, the first problem which I have here is the first problem in the book at the end of the chapter. You have several operations A, B, C, D, and operation 1 has only one machine. Now B has multiple machines. So basically products are going from A and B, whichever machine is available, they will go to B, and then they will go to C, and then from C, they will go to D, whichever machine is available as depicted here. And design capacity is given and planned utilization is given. And your goal is to figure out what is the maximum actual capacity for the system comprising A, B, C, D, and what is the effective capacity. So I took all this information and put it on Excel. And so you have A, B, C, D. A has one machine and B has 4 machines. Each machine has a design capacity of 180 and so on and so forth. This is how the information was given. I just copied and pasted in Excel. So design capacity is going to be simply for A is simply this number. For B, it is really sum of these numbers. Now, so I'll do it differently so that I don't have to copy. I'm going to copy this, Control C. I'm just trying to be a little lazy. All right, or efficient, if you want to call it. Control V and enter, and we got this number. Oops, it was at the wrong place. I'm going to move it over here. Just make sure it is 100. These numbers are added. Perfect. This is going to be the same number as 350. And this is going to be, again, the same idea. I'm going to copy this over here. Control C. The advantage of what I did rather than typing is that, if I type, I'm prone to make mistakes. Here, at least, I'm not making mistakes, okay? And then your planned capacity is 80%, 77%, 95%, and 72.5%, 0.80, or if you want all of them to have 3 decimals, you can increase the decimal as you know this. All right. So 80%, 77%, 95, and 22. So overall capacity can be simply, you take this number, so you can add stage 1, you can handle 400, stage 2, you can handle total 455, and so on. So effective capacity will be simply product of this number, and I'm sorry, it should be this number. I'm going to fix it. This number and this number, okay? So if I do that, I get these numbers here. And effective capacity, let's just do this. So system capacity, what is the system capacity by design? It looks like since C is the bottleneck, that will dictate how much you can produce. So this really the smallest number, 350 is what that can flow through the system. So design capacity is going to be simply minimum of these numbers here. And 350. And the same thing, you can just copy the formula here and apply it here, Control copy C, Control V, pasting, and it does the same thing. It just figures out the smallest number. So effective system capacity is 308.12. And that's problem 1. That's all they are asking you to do in problem number 1, I believe. Okay. Let's see. Okay. All right. I just want to have the problem available somewhere and make sure that there's nothing I'm missing in this problem that they want us to do. Okay. All right. So really, in this example, in design capacity, C dictates how much that can flow through. And in the effective capacity, really is the D, which is dictating how much can flow through the system, because C has a very high planned utilization, but D has lower planned utilization, and that is why that is the one that is affecting. All right, let's move on to number 2. Problem number 2, you are making 3 different products, and the demand for each product is these times, these many units, and each product takes this much time per unit. So you need to figure out basically these, how many equipments or setup you will need. It says assembly line assembling operates 2 8-hour shift for 275 days. So 8-hour shift, 275 days, and you need to figure out how many assembly lines do you need to have. It also assumes that there is no setup time. The setup time is very negligible. They have not given us anything. So I just put the same information here. This 1,500, 1,800, 8,000, 15,000, 12,000. These are the minutes processing time in minutes. So total time needed is simply I like this formula very much, called sum product. And I'm going to take these numbers and multiply them by these numbers. It will multiply respective numbers and add them up. So these are the total number of minutes you need. Now, each assembly line is capable of giving you 2 shifts, okay? For 275 days, 8 hours a day, and 60 minutes. I'm converting them into minutes because the task times, total processing time needed is in minutes. So again, 2 shifts a day, 275 days per year, 8 hours per shift, and 60 minutes, converting that into minutes. And that number is given here. So now you need to find out how many lines do you need. Well, you need 561,000 minutes, and you have only 264,000 minutes per shift. So you will need more than one. And if you do this calculation, you will get this divided by this number, and that's 2.125. And you know that even though you need only 2.125, you have to have a whole number. You always round it up. So I'm going to take this formula and just say round up and comma 0. And that tells you you will need 3 processing lines. So that's problem number 3. We did just number 3. Number 5 is very much similar to number 3 problem, but here they are telling you that you also have setup time, and it looks like every time you load up the machines, you can load up only 10 bikes per lot, and each time you take those 10 things off and then set up another machine, raw material, equipment, etc. It takes 50 minutes to set up. So how will you do this problem? Well, you will have the processing time, plus you will have to worry about the setup time. So this is what I have. All right, I'm going to just delete all this information. So I'll show you how to calculate these things. All right, so 1,400, these are the demand, these are the numbers which I got straight from the problem. So total processing time is an easy one. You basically take this number, annual demand, and multiply it by processing time, and you have now processing times. Okay, now how many times you have to set up? Well, it looks like you are making 14,000 units, and every time you set up, you can do only 10. So you will have to 14,000 divided by 10. 1,400 setups you will have to do. So you take this 14,000 divided by lot size of 10, and you get 1,400. And then of course you can, double click on this thing, and it fills up everything here. All right. So total setup time. How much total setup time do you need? Well, that's easy one again. You have each setup requires this much time, 50 minutes, and you need 1,400 setups. So that's a setup time. And double click, and it fills up nicely. Now you can figure out the processing time, this stuff, and add up with setup time. That's the time your money is going, your production line is going to be occupied. So is equal to sum this one, and this one, and double click, it fills it up. And then I have a total sum that this is the total amount of time you will need. Each processing time per line, it should say, actually, it should say per line, not shift, is you have this is the annual processing time. This is the annual number of minutes you need. So each machine will operate for 2 shifts a day. And total, they will provide 2,000 hours, which is 60 times multiplied by 60. And if I did that, that tells me each machine is capable of giving me 240,000. So how many machines I need is the same exact thing. I divided this by 24000 and rounded it up to the whole number. So no decimals, 0 decimals. Okay. And I got this number. All right. That's number 3. Let's move on to a different kind of problem. Number 8. Number 8 is I'm kind of a little bit disappointed with this book because I don't know, why don't they use the standard notation that is used by the world? The Little's law says L is equal to lambda times W, where lambda is the arrival rate, at what rate things are arriving, and W is the average wait time in the system. It didn't show, it's not copying it. Yeah, as the average time an item spends in the system, average wait time in the system, or average flow through the system, and L is the number of entities that will be sitting in the system, is the average number of items or entities, people, equipment, machine, whatever that may be. And in this example, they are telling you what, and the book uses this formula, F is equal to Y over TH. It's the same formula. It's I is really L, and F is really the wait time, and TH is the throughput time, which is the arrival rate or service rate, whatever they want to call it. Okay, so in this example, they are telling you that the average inventory or number in system L is equal to 450,000. Throughput, you can process 325,000 DVDs in this example. So basically, they're telling you, hey, there are some DVDs are coming in the sorting facility. They come in, you open, you check for cleanliness and scratches and cracks, etc. You put them in the envelope and ship it out, and it looks like people are renting it, people are returning the DVDs, and this is probably an older example when Netflix used to rent DVDs which arrived in mail. Anyway, so you can handle 325,000 per shift. Shift is 8 hours long, and 450 items are sitting in the system. So that you need to figure out what is the average wait time. So in this example, they've given you L, they've given you the arrival rate. They want you to know the W, or flow through time. So same thing, is the same formula. I like the standard formula better. Anyway, so the flow is going to be basically the number of items sitting with you at any given time in the system divided by the average throughput rate, which again is derived from the same formula. It's just rearranged. The W is equal to lambda L divided by lambda. That's what it is. Okay, so I did that. I just took this number. The 8-hour shift has 320, throughput time is this much. Inventory is this much. So inventory divided by throughput time. And that tells me that on an average, DVD spends about 1.384 shifts, more than one shift. It has to sit there before it gets shipped out. And since shift is 8 hours, so 8 hour times this number. If you take 8 hours, multiply this by this number, you'll get about 11 hours. So if they want, if they want this to be no more than 6 hours, if suppose they want this to be 6 hours, what do they have to do? Well, to achieve 6 hour wait time, all they have to do is, a little bit of math here. The throughput rate has to be increased. So throughput rate in that case, the throughput rate has to be increased, or the average flow time has to be decreased, which is same as throughput rate is increasing. So the throughput rate TH is going to be equal to I times F. Okay, and they want really the wait time to be 6, wait the time spent in the system to be 6 hours. Arrival rate is something you cannot do anything about. So the only thing is that you will have to just recalculate this number. Okay. All right. So they want to now desired wait time. They want to cut it down from 11 hours to 6 hours. So what do they have to do? Well, the only thing they can do is process them at a faster rate. 325,000 units per shift is not acceptable. So they have to increase it. So one thing is we need to figure out what is, if 6 hour translates into how many shifts? That's like 6/8 shift, less than one shift. So let's calculate the shift, which is, in terms of shift, the desired shift when it should be processed is going to be 6 divided by 8. Okay. What happened here? Oh, because I put desired wait time is 6. I should have put it into a different cell. So bad practice. All right, let's do this. Move it over here. And I'm going to just take the 6 out and keep 6 by separate so that I can do these kinds of things easily. So new throughput time is going to be basically new wait time in the system is going to be, or flow time is going to be, I should call it new, is going to be 6 divided by shift is for 8 hours, 0.75. And for that to happen, you have to process at a much faster rate or much higher rate. So let's calculate the new, what will be the new throughput rate is simply, this is the average quantity divided by this new flow time. And that tells you that they have to increase their capacity so that they can handle 6,000 units per day. All right, moving on to next problem. This is where you need to figure out what is the processing time, what is the wait time. Look at this one. This is the formula for wait time, I will assume. And they have given you this information. So they're telling you average processing time is 10, but the standard deviation of processing time is 50. That's humongous. That means a lot of people, they come for, their questions get answered in seconds or things get processed and some take forever. So a lot of variability in processing time. What about arrival time? Arrival time, arriving at the rate of 10, but look at the standard deviation of arrival. Oh my, this is even humongous, even bigger. So a lot of variability, for hours, people don't show up, and then for within a certain time, a lot of them show up within very short time period. And whenever you have these kinds of variability, the average wait time in the system will increase. So the wait time is going to be calculated using something known as the coefficient of variation, squares of arrival as well as departure. You take the average of those two squares and multiply it by U, the average utilization, divided by 1 minus U times the average processing time. This formula we have to apply. So I will calculate first the CP, which is 50 divided by 10. The standard deviation, coefficient of variation for processing is 5. That's like a big number. And arrival is even bigger. Oh my, this is huge. Okay. The company has decided that, if they have the workers sitting around, whatever, they want the workers to be utilized 80% of the time. So they have come up with 80% rule, 80% thing. All right, given all this, what is the average wait time? Well, look at this number. You have 10, I'm just applying this formula, and you have to be very careful when you are applying the formula here. You have to use parentheses correctly. Coefficient of variation for process, square them. Coefficient of arrival, square them. Find the average, multiply it by the utilization divided by 1 minus utilization. Again, using parentheses is very critical. Multiply that by the average processing time, and if you do that, you get 2,400 minutes. Now, if what can you do? What can you control? Is the question. Well, sometimes you can control the arrival rate by giving appointment. Hopefully, you can reduce the big variation in arrival rate. Processing time and the variability in processing time can be controlled somewhat by using self answering system or frequently asked questions, or using some standardization of process. You can control somewhat variability in the processing time and reduce the standard deviation there, and therefore coefficient of variation, reduce that number. The thing which is under your control is the average utilization. Maybe put more resources so that the average utilization is not 80% of all the people who are serving, but maybe it is 70% or 60%. So you will have to increase staffing if you want to cut down the wait time. All right. Let me go back and see what do they want here in this problem. Oh, sorry. I'm going to pause here recording. Alt P. So if they want to, so if you look at the average wait time, it's more than 40 hours. And if they want to cut it down to 24 hours, things under their control, which they can easily reduce or affect, is the average utilization. If they put more people, the average utilization will go down a little bit, and that may help. The other thing which can do is maybe they reduce the processing time. The other time they can do is reduce the arrival rate by giving them appointments. So these are some of the things they can do. Arrival variation can be cut down, maybe cut down with using appointment. Processing time can be cut down, or utilization can be decreased by putting more work. So they are not busy 80%, that high percentage of time. So that is basically the answer.